Hello, everyone. My name is Macarena Garcia Marin. And first of all, I wanted to thank you all for joining me today to talk about the James Webb Space Telescope and the incredible science that it's delivering. I also wanted to thank the organizers for giving me the opportunity to be here with you today. So let's get started. Let me begin by saying that JWST, it's an absolutely fantastic telescope that has surpassed our expectations. The images are twice as sharp, the optics are more stable than expected, and the instruments are more sensitive than we thought they would be pre-launch. We have fuel for about more than 20 years, and the telescope is now on its third year of mission. It is truly, the bottom line is that JWST is truly fulfilling its promise of revolutionizing astronomy. So let's talk a little bit about the light. Telescopes are machines to collect light, and astronomers will use that information from the light to try and understand all the astronomical objects and the universe around us. This diagram shows an image of Isaac Newton at the time where he used a prism to filter the sunlight and disperse it in its colors. And because it is in the visible, we see blues and reds and yellows, etc. So this is a visible rainbow. But of course, we know that the light is not just the visible. The light has radio and emits in microwave, infrared, visible, ultraviolet, X-ray, gamma rays. So there is a lot of information that comes through the light. And the visible, the light we can see with our eyes, it's a very small portion of it. What does this mean for astronomical objects? Well, it truly means that because the universe emits light at all wavelengths, we need telescopes at all wavelengths to really get a full picture of the complexity and the nature of these objects that surround us. In the case of the James Webb Space Telescope, we use infrared light. So what is infrared light? This is an example of two pictures of, we have meerkats and we have a crocodile, and this is how we see them with our own eyes. This is visible light. If we now put on our infrared goggles, this is how they look like. The meerkats, they are warm blood animals, so they are glowing, they're shining in the infrared, whereas the crocodile, being a colder blood animal, it's really more muted and more demure. So this is now giving the hint that infrared is an excellent way of measuring temperature, and every object in the universe that has any temperature above zero emits in the infrared, which makes it an excellent tool to observe things like distant galaxies. So let's have another example. This is a firefighter, and the firefighter in this picture is surrounded by a cloud of smoke. So what would the firefighter see with infrared light? This is what it would see. It would have the ability of seeing through that cloud of dust and smoke and really see a person lying in the floor because it's glowing, it is really warm, and the temperature is making it very obvious. So this is, again, one of the powers of the infrared. You can see things, for instance, through dust, and you can also see the dust itself glowing in the dark. Let's have a practical example. This is a very beautiful galaxy, a spiral galaxy, as seen with the Hubble Space Telescope. This is visible, and we see all this glowing star formation. We see lines of dust, all those dark brownish lines. These are sites where dust is blocking the visible light. We see the nucleus. So it is a really, truly beautiful galaxy. But when you look at it in the infrared, this is how it looks like. It has now a more ghostly appearance. And if we go a bit back and forth, you will see that everything that was dark in this image is now glowing in the infrared. So all that dust, that it is being the site of new stars being formed, it is now glowing in the dark. At the same time, we have all these cavities and sort of bubbles across the galaxy, and these are indications of the effect that the cycle of star formation has in galaxies, like clearing out all these spaces. So truly, infrared gives us a fresh take and a fresh view and a different type of information in this galaxy. JWST has 4 instruments on board, and they use different techniques to collect light and to provide information, but we're going to focus today on the 2 main ones, spectroscopy and imaging. So let's get started with imaging. JWST, as I said, does imaging. So cameras select light using filters. So in this example, we just have visible light with the usual colors. If we use a red filter, the red filter will absorb all colors except red, which means that we would get a red image of the object we're looking at. Of course, for JWST, the filter would select an infrared color, and we would be able to combine that color with other infrared colors. So it's truly a selection process that is very targeted to specific colors that we want to observe. What is a spectroscopy? JWST does spectroscopy, but what is a spectra? We saw before the rainbow created by Newton with a prism, and now we're seeing a rainbow here as well, but we also know that some materials, they do absorb light. They have that characteristic of absorbing portions of light. And the way this is represented here is with the vertical black lines. We also know that some materials emit light, and this is represented here as white vertical lines. So astronomers plot this absorption and emission lines as spectra, and this is what is represented here. All the dips are representing the absorption lines, and the peaks are representing the emission lines. And this is really a practical way of understanding the information we're looking at. And this is the way you do it in reality. So you have here this beautiful set of galaxies, and for two of them, we're taking a spectra, and you see there the light being dispersed. So in the dispersion of that light, we're finding out that actually they have oxygen and they have hydrogen. And not only that, but we're seeing that the hydrogen and oxygen are precisely at the same location. And this is an indication that we are looking at mirror images of the same object. We're going to talk about this particular object later on. But the point I want to bring here is that spectrum, it's equivalent to incredible science discovery. It really opens a new space because you can understand the composition. In this case, you know this object has oxygen and hydrogen. You can understand the temperature and the pressure and dynamics and how gas moves in galaxies and how stars evolve, etc., etc. So it's a wealth of information that we have access to. And in the case of JWST, about 75% of the time, it is doing a spectroscopy. So it's really a lot of information to unpack. Let's talk a little bit about cosmological redshift. What is redshift? So cosmological redshift is really the rate at which the universe is expanding. So we know the universe expands. So that means that faraway galaxies, they are moving even farther away from us. How do we interpret that with a spectra? This is a nearby star, and here we're just depicting a spectra with a set of absorption lines, again as vertical lines. If we look at a nearby galaxy and we observe the same lines, they will be slightly moved because the galaxy is farther away in a universe that is expanding, so the lines are moving slightly to the right, slightly to redder colors. If we look at a more distant galaxy, the same lines are more shifted. And finally, if you look at a truly distant galaxy, that in this case it's very small and it's supposed to be really far away, the same lines are truly moved to the right. And in this case, you see here there that the last line could, if the galaxy was farther away, would easily be out of the range. And this is how it looks in real life. So in this plot, it's a beautiful image where each horizontal line represents a spectra of one galaxy. We have more than 1,000 here. The lines on the bottom represent galaxies that are closer to us. The lines on top are galaxies that are farther away from us. And you see how that emission line, that bright line, for all of them, it's just everything is moving to the right because everything is redshifted, because as you go up, the objects are farther away. And again, for each of them, you would have, in this case, information of hydrogen and nitrogen and sulfur and oxygen. So again, a wealth of information to unpack on all the objects. So what is JWST in a nutshell? It's a large infrared optimized telescope that is located 1 million miles away from Earth in a very stable orbit, kind of very easy to maintain. It is protected by, it has a sun shield, as you can see in this depiction, and the function of the sun shield is to protect it from the radiation of the sun and the Earth. And the reason is because you don't want that heat to affect the measurements of the infrared, so you have to keep it really, really cold. It's also big. Why is it important? Here you have a comparison between the JWST and the HST mirror, so significantly larger. Why does that matter? Well, the size of a mirror in a telescope determines the level of detail and the sensitivity, or how faint objects, like how much fainter objects you can see, essentially. And this is an example. This is a region of the sky observed by the WISE telescope on the infrared. And this was, this telescope had a primary mirror that measured about 40 centimeters. So there's not a lot of resolution, essentially. If you look at the same region of the sky with a Spitzer that had 80 centimeters, you see that you start to resolve more stars, you see fainter objects, and it really looks a lot better. With JWST and 6.5 meters mirror, this is what you see. Truly spectacular resolution. Things that are points or blurs on other images here are resolved like stars, and all that extended emission, all that sort of faint veiled structures you see, this is dust. This is dust that is glowing there and it's ready to be measured and understood. So that's why, in this case, being large matters. Let's begin talking a little bit about science with JWST. And typically we talk about 4 pillars of science. The first one is the study of the early universe. And by that I mean the study of the very first galaxies and stars that were forming the universe. And this is the main reason why this telescope came to be, because you need the infrared to observe that very, very, very far away objects that, with which the universe started. So we have the first galaxies that are formed, and these galaxies evolve in time. So the second pillar of science for JWST is the assembly of galaxies over time, which means how did those early galaxies evolve to become the galaxies we have today, including our own Milky Way. Galaxies are essentially the neighborhoods where stars live and evolve and happen to be. So the third pillar of science for JWST is the birth of stars and protoplanetary systems, because many stars end up forming planets around them. And finally, the study of planetary systems and the origin of life is the fourth pillar of creation. So what we're seeing here is that essentially with JWST, we can observe everything from the very early universe to our own solar system. So from Mars and out, everything is seen. And it's an observatory that is so flexible that essentially any size you can dream about in the infrared, you can attempt it, and you can do it with JWST. And we're going to start seeing some results starting from the beginning, the exploration of the early universe with Webb. This is an image I'm sure all of you have seen, and this was the first early release observation that was released, and it's a really beautiful picture of a cluster of galaxies that is in the center. Clusters of galaxies are really interesting objects because they act as natural telescopes. They are so incredibly massive that even the light from the objects that are behind, it's sort of distorted, that it bends around them. And that ends up, because it sort of goes around the cluster, it ends up creating mirror images of the objects behind. And not only they are mirror images, but they are also magnified. So to the power of Webb, you have to add the power of nature, and you end up magnifying all these little arcs you can see are galaxies that are behind the cluster, much farther away, and we can clearly see not only once, but 2 or 3 times, depending on the configuration. Let's zoom in a little bit so you can enjoy a closer view of this. So all those arches are what I mean by magnification and gravitational lensing. And you see here how, when you keep looking at this image, there are so many galaxies. I think there is no better way of describing it. There's just so many of them, and it's a very nice representation of what you get in an astronomical picture. All of these galaxies are located at different times and distances, but we see them in projection. There are thousands of them, and it's a truly fantastic image. And you also have stars. Stars are really easy to spot because they have the diffraction peaks. So what can we learn if we then take spectra of some of these galaxies? Well, as we talked about before, you can learn about their chemical composition. And in this case, we're focusing on hydrogen and oxygen. The galaxy on top is 11.3 billion years old. The second galaxy is 12.6 billion years old. And there you can see what we discussed before, how the lines shift because the galaxy is farther away. We're seeing the same hydrogen and oxygen lines. The third galaxy is even farther away, and the next galaxy it's a little bit farther away. Remember, the universe is about 3.8 billion years old. So are these the oldest galaxies JWST has seen? And the answer is no. The oldest one we've seen to date is this one. It's called JWST Z140. And in this little zoom, on the image on top, there are actually two galaxies. The one on top, the white one in projection, that is closer to us. The farthest away galaxy we've measured to date is the one in the bottom, the red one. And this galaxy existed about 300 million years after the Big Bang. So in a very, very young universe. If we pack the life of the universe in a single year, in a single calendar year, this galaxy existed at around January 7th. So it's really, really, really young. And it's young, but at the same time, it has had the time to have some chemical enrichment and have some sort of evolution. So certainly it is not the first galaxy that was created, but it's the oldest one we've seen to date. And that's a really exciting result. So let's have a look at how do we study galaxies over time and what happened with these galaxies. So one process that galaxies go over very frequently is the process of interaction and merging. This is an example of them. In this case, the galaxy to the left is not part of this group. It is closer to us, but the projection makes it look as if it was. This is a Stephan's quintet. And you see the galaxies to the right, how they are distorted, they have plumes, they have lots of structure, they are creating shock fronts that trigger star formation, and this is all part of a very common process of interaction and merging that all galaxies go through at some point. If we look at a different infrared color or colors, this is what we see. We see dust. We see sites of young star formation. And at the top galaxy, we see a point source in the center that is an AGN, an active galactic nucleus. Essentially, it's a black hole that is actively eating, if you want, material around and releasing lots of energy. If we then use spectroscopy to look at the gas around that black hole, we see that it has iron and argon and sulfur and neon. So again, lots of chemically rich materials, and we are able to understand what are they and what are they doing and how they move around that black hole. This is another example of a collection of galaxies to illustrate how JWST, with its infrared powers, allows us to see all these structures and to really put them in the context of how does star formation impact galaxies. So again, galaxies, there are many stars in galaxies. So stars live within galaxies. And how are they born and how do they die? This is a very nice Spitzer image of a gigantic cloud where many stars are being formed. This is a site of active star formation. And here at the center, this is Rho Ophiuchi. And this is how you can see it. This is how it looks like with JWST. Again, truly a spectacular image. This is a site of a star formation where about 50 stars, very similar in mass to our sun, are forming. The star at the center, slightly more massive, it's very young. It's just sort of, it's getting out of its cocoon of dust and material, and it's really getting out of, starting its life essentially as a star. And it is illuminating all the material around. That's why you have that sort of yellow, beautiful cocoon of dust around it. If we have a little bit of a tour, all these red structures, these are hydrogen jets that are created by protostars. So stars, they do form in disks. And as you can see in the image next, this one that looks like a bat, pretty much. At the center of that, there is a star being formed. The stars form in a disk. And the disk, at the beginning, you don't see the star because the disk is just obscuring and there's a lot of material, but you see those jets, very powerful, illuminated, sort of going like that from the protostar, and in this case it's a hydrogen jet. So again, the level of detail this image is providing, it is truly spectacular, and it really helps understanding how stars are born. We said here these are about 50 stars similar in mass to our sun. So what is the future of these stars? So stars like our sun, they die as planetary nebula. So at some point they become what we call a red giant. And in the attempt of maintaining its equilibrium, they start shedding the outer shells. And in that shedding, they enrich the environment around. So stars are the chemical factories, the factories where the chemical elements are produced. At the beginning of the universe, after the Big Bang, everything was mostly hydrogen and helium. All the rest of the elements are composed in stars. And when the stars die and when they shed layers and they sort of enrich the elements and they create inside them, inside their nuclear power station, they create new materials. When the stars are a lot more massive than our sun, let's say 10, 20 solar masses, they explode as supernova. And in that explosion, again, they create heavier materials and they shock the environment. So that means that potential clouds of star or interstellar medium, it gets shocked and compressed and can even trigger future star formation. But also the elements and all the materials from the star, it enriches the environment around, and it's the resource that you have to create new generations of stars. Finally, this is a very beautiful example and very recent. This is a cluster in the Small Magellanic Cloud. It is a nearby galaxy, really small and really close. And the special thing about this image is that the team that produced it, they have found candidates of brown dwarfs for the first time outside our galaxy. So brown dwarfs are somehow some objects that are between planets and stars. They are really not planets because they don't orbit around the stars. They are free floating, but they are also not stars because they don't have enough mass and enough power, if you want, to start nuclear reactions. They don't burn hydrogen in their core. So it's like something in between. And in this image, for the first time, they have detected candidates of brown dwarfs outside our galaxy, which is truly a feat, and it's really thanks to the power of JWST, the power of resolution and sensitivity. So the stars often form planets around, and JWST also explores that in a lot of detail. This is another example of a region where stars are being formed. And you see in the zooming at the bottom right, that's a star with a protoplanetary disk. So that means that around the star, there are materials and enough potentially planets can form in there. And the reason why it is not like a nice disk, it looks like misshaped almost. That is because all the stars radiating from the top part essentially are creating winds and the radiation, and that is really impacting the star and the forming the disk. But this is a place of potential planetary formation. So again, why are we interested in that? Why are we characterizing, in this case, water abundance? Well, the truth is that planets form in disks around the stars. So the more we understand the conditions that allow the formation of planets, the better we can understand how planets are formed and how our solar system was formed, etc., etc. So in this case, this is a study that compares compact disks versus not so compact disks and warm water and cool water. And it's all about what materials are available to create planets and how they move within the disk and how they sort of how is it possible from a disk to end up having a planetary system? And this is, again, where spectroscopy gives a really incredible, rich set of information for understanding all of this. So once a planet is formed, it orbits around a star. And this illustration depicts a technique called transiting exoplanets. So you see, when the planet goes in front of the star, the light of the star is dimmed, and it's also filtered through the atmosphere of the planet. And that's a tool to learn about the composition of planet atmospheres. So JWST has detected many molecules in giant planets, and in the following, we're going to talk about two big type of families of planets, if you want: giant gas planets and rocky exoplanets and rocky exoplanets. So this is an example of giant gas planet atmospheres, and as I was saying, JWST has detected many, many molecules of them, many of them for the first time. So it's really producing a catalog of chemical abundances and chemical composition and atmospheric compositions for different exoplanets. It's also has been also able to measure day and night variations in temperature in an exoplanet, which is truly a difficult measurement. It really tells us about how dynamic the atmosphere in the exoplanet is, because you can measure variations from day to night. So truly, yeah, it's amazing. And finally, JWST has also measured an atmosphere in a rocky exoplanet, which again, it's a very hard measurement to do, because planets are very small. The amount of light that filters through the atmosphere is really tiny, but with enough stability as JWST has, and with enough sensitivity and control of the data, you can actually do this measurement. So this was, in my opinion, one of the excellent recent discoveries of JWST in exoplanets. Finally, JWST explores our solar system. And really, you could think, well, solar system, very bright, very big, very close. Why do you need such a big telescope? And the answer is in this beautiful Jupiter image, because the detail, this is an aurora, the detail with which you can study the closest planets we have to us, it is unheard of in the infrared. So here you have the atmosphere, you see the clouds and turbulences, and you see how beautiful the famous big red spot of Jupiter is. And actually, when you look at it with other JWST instruments, the recent results show that they have the great red spot has a cold heart. So it is cold, but it also has patchy clouds. So it's really opening the window to fully understanding, or let's say, improving all of our understanding of the dynamic of this very close solar system planet. This is another example. In this case, this is Uranus with all its satellites, or most of its satellites. And if we zoom in, again, you can see with the detail with which you can measure it, but not only that, you see so many galaxies in the background. And again, we go back to the projection effect and the detail with which you can observe it. So in this case, not only you're seeing a very close by solar system planet with its satellite and rings, etc., but you also see galaxies in the background. And if we zoom in into Uranus, we can see clouds in the atmosphere, we can see the polar cap, and we can see beautifully detailed all those rings. Never seen before in this detail in the infrared. Finally, JWST has very recently studied centaurs, and centaurs are objects that orbit around the sun, and they are placed between Jupiter and Neptune. And these objects are really, you can think of them as leftovers of this early solar system materials that were available for forming planets. And they are very cold, so they are sort of preserving that very young, very early stages of the solar system. And in this case, the team has seen that gas is sweeping out from this center in the form of jets. So it's allowing to study things like CO and CO2, and really understanding what are the materials and the products that were available when the solar system was in its infancy. So I'm going to leave you with this very nice video based on real data. This galaxy is called the penguin and the egg for obvious reasons. This was our second year anniversary image. And it's just a very nice overview and detailed exposure of emerging galaxy that again gives you a sense of the incredible. I feel we are all incredibly lucky to be able to have this beautiful telescope providing this incredible data and images and really enhancing our knowledge of the universe and charming all of us with all the data. So my time is up, and I just wanted to thank you for your attention, and hopefully we'll talk about JWST and its science very soon. Thank you.